What if everything we thought we knew about the cosmos was a comfortable lie, a set of rules written for a quiet and predictable universe, and we are about to witness the exception that shatters them all? This isn't a prologue to a science fiction novel. This is the reality unfolding in the dark control rooms of observatories and on the flickering data screens of the world's most powerful telescopes right now. It began in the summer of 2025, a pinpoint of light where no light should have been, discovered by the vigilant Pan-STARRS telescope in Hawaii. They designated it 3I Atlas, the third confirmed interstellar visitor to our solar system, following the enigmatic Oumuamua and the more predictable comet Borisov. Before we dive deeper, I want to know, where in the world are you joining us from and what time is it there right now? Drop a comment below. I read everyone. This story is unfolding by the hour, and you won't want to miss a single update. If you're as captivated by this cosmic mystery as I am, make sure to subscribe and hit the notification bell. You are the reason we can chase stories like this to the edge of understanding. Thank you for having our back. Now, let's begin. Initially, it was catalogued as just another frozen wanderer from the vastness between stars, a relic of some distant alien solar system, destined to swing past our sun, gather a brief footnote in astronomical journals, and vanish forever back into the deep freeze. The predictions were clear, grounded in decades of cometary science. It would follow a hyperbolic trajectory. It would brighten as it approached the solar furnace. Its ices would sublimate, forming a faint coma and tail, and its path would be bent ever so slightly by these natural jets. It was supposed to be predictable, quantifiable, and above all, safe. A cosmic curiosity, nothing more. But within weeks, the data began to whisper of something else entirely. The whispers soon became a roar. 3I Atlas did not follow the script. It began to accelerate, not with the gentle, predictable push of outgassing, but with a deliberation that made the equations break. Its brightness pulsed in rhythms that felt anything but random. The math, the very physics we use to navigate probes to the outer planets and understand the dance of galaxies, began to fail when applied to this single, silent traveler. Astronomers, a community built on calm analysis, began using a different word: anomaly. But what if this anomaly is more? What if we are witnessing the opening act of a Black Swan event, a occurrence so rare, so profoundly unpredictable, that it rewrites the rules of reality after it occurs? This is the story of 3I Atlas, and it is happening in real time. As you watch this, the object is rounding the sun, and scientists are scrambling. Tonight, we will pull back the layers of this mystery, from the hard, unsettling data to the speculative, terrifying possibilities. We will ask the question no one in authority is asking out loud. What if Atlas isn't just passing through? What if its arrival is the beginning of something we cannot yet name? To understand why 3I Atlas is so deeply unsettling, we must first establish a baseline of normalcy. We need to know what the playbook looks like before we can see how thoroughly this object is tearing it to pieces. For centuries, we have studied comets, the icy time capsules of our solar system. We've built robust, reliable models for their behavior. When a comet journeys from the outer darkness into the warmth of the inner solar system, solar radiation heats its frozen surface. Ices, primarily water, but also carbon dioxide, carbon monoxide, and others, sublimate, turning directly from solid to gas without becoming liquid. This gas erupts through cracks and vents in the comet's rocky nucleus, carrying with it countless dust particles. This creates the comet's signature features, the coma, a glowing, nebulous atmosphere around the nucleus, and often the magnificent tails that can stretch for millions of miles, always pointing away from the sun's radiation pressure. This process of outgassing is not just for show. It acts as a natural propulsion system. These jets of gas function like tiny, erratic rocket engines, imparting a slight push that alters the comet's trajectory from a path dictated purely by gravity. This is called non-gravitational acceleration, and it is a predictable, calculable force. Given the comet's size, composition, and distance from the Sun, we can model precisely how much it should deviate from its gravitational path. Furthermore, a comet's brightness follows a predictable power law as it approaches the Sun. The closer it gets, the more active it becomes and the brighter it shines. Scientists quantify this relationship with the heliocentric distance exponent, a number that typically falls within a known, comfortable range. So the baseline is this: outgassing increases with solar proximity. Brightness follows a predictable curve. Non-gravitational forces match the observed outgassing rates, and photometric behavior aligns with distance. It is a simple, testable, and until now, reliable framework that has allowed us to understand everything from Halley's Comet to the thousands of denizens of the Kuiper Belt and Oort cloud. This is the universe playing by the rules we have painstakingly decoded. Now, let's place 3i Atlas against this backdrop of expectation and watch the dissonance unfold. The first major crack in the narrative appeared when astronomers measured its activity at a distance of approximately 2.9 astronomical units from the Sun, that is nearly 3 times the distance from the Earth to the Sun. At this vast distance, deep in the frozen outskirts of the asteroid belt, most comets are dormant, locked in a deep freeze, their surfaces far too cold for significant sublimation. But 3i Atlas was not dormant. It was violently active, shedding water vapor at a rate typically seen in comets much closer to the Sun, as if someone had turned on a fire hose in the heart of a deep freeze. This was the first stark deviation. Then, the James Webb Space Telescope, JWST, turned its infrared gaze toward the object, and the data it returned was even more peculiar. The coma of 3i Atlas, that cloud of gas and dust, was not dominated by water vapor, as is the case with the overwhelming majority of comets we have ever studied. Instead, it was dominated by carbon dioxide. The ratio of CO2 to water was measured at approximately 8:1. To put this in perspective, most solar system comets have ratios closer to 1:10, or even 1:20, where water is the king of volatiles. Here, in this interstellar visitor, carbon dioxide reigns supreme. This makes it one of the most CO2-rich comets ever observed in the history of cometary science. We have studied hundreds of comets, built catalogues of their chemistry, constructed models of their formation, and then along comes 3i Atlas from a star system we will never know, and it shatters the pattern. The questions began to mount. If this is a natural body of ice and rock, why is it so active so far from the Sun's warmth? Why is its chemical fingerprint so extreme, so alien to our experience? The comfortable label of comet was beginning to feel ill-fitting, a square peg being forced into a round hole by the sheer weight of our own expectations. As if the anomalous activity and bizarre chemistry weren't enough, the very path of 3i Atlas through our solar system adds another layer of statistical unease. The object is on a hyperbolic orbit with an eccentricity greater than 1, confirming its interstellar origin and its ultimate fate to escape the Sun's gravity forever. It is also moving retrograde, meaning it orbits the Sun in the opposite direction of the planets, a trait shared by Oumuamua and not uncommon for interstellar objects. However, its orbital inclination, the angle of its path relative to the flat plane of the solar system where the planets orbit, known as the ecliptic, is only about 5 degrees. This means it came in almost perfectly aligned with our planetary disk. Statistically, this is unusual. We expect interstellar objects to arrive from random angles from all over the celestial sphere. The fact that this one, like Oumuamua before it, slipped in almost through the front door, nearly along the plane of our own planets, is, well, coincidental, maybe. But in science, especially in astronomy, coincidences often hide deeper truths, clues we are not yet equipped to understand. Its perihelion, its closest approach to the Sun, occurred on October 29, 2025. As you hear this, it is on its outbound journey, racing away. But its journey through our neighborhood was far from isolated. On October 3, 2025, it passed within roughly 0.19 AU of Mars, a close shave by astronomical standards, closer than many near-Earth asteroid encounters. Later, it will pass Venus and have a significant encounter with Jupiter in March 2026. These close passes do not pose a direct collision risk with the planets, but they raise critical questions about gravitational interactions within the delicate clockwork of our solar system. Could this object's gravity, however slight, perturb the orbits of smaller bodies, of asteroids or Mars's moons, in a way that cascades over time? This question of gravitational domino effects is one we will return to, for it represents one of the most plausible, yet most delayed, threat scenarios associated with this visitor. Here is where the mystery deepens into the realm of the profoundly strange, where the data doesn't just deviate, it actively contradicts itself. We have established that 3I Atlas is outgassing prodigiously, spewing water and carbon dioxide into space. According to every model, this powerful outgassing should be acting like a thruster, pushing the object off its purely gravitational trajectory in a significant and measurable way, the non-gravitational acceleration we discussed. Yet, when astronomers like Harvard's Avi Loeb, the same scientist who famously suggested Oumuamua could be a light sail, crunched the numbers, they found a glaring discrepancy. The observed non-gravitational acceleration is much, much weaker than the models predict. It is barely there. Think about that for a moment. The object is vomiting gas and dust into space, but it's not being pushed around by it in the way it should be. This creates a fundamental tension in the data. Loeb and others have pointed out that this suggests one of two things, both problematic. First, perhaps the nucleus of 3I Atlas is incredibly massive or dense. If the outgassing jets are pushing against a much larger mass than anticipated, the resulting acceleration would be small. But if the nucleus is that large, then the outgassing rates, while high, become less absurd in terms of the force exerted. The second option is that the nucleus is small, but the outgassing is somehow not imparting much momentum, perhaps because the ejected material is very slow-moving. The size estimates for the nucleus are all over the map, ranging from 0.3 kilometers to a staggering 5.6 kilometers in diameter, depending on assumptions about its reflectivity and composition. This massive uncertainty propagates through every calculation. If it's small, the outgassing is absurdly violent for its size. If it's large, the lack of acceleration is absurd. We are left with absurdity either way. Something is missing from the equation. This core tension, the disconnect between action and reaction, is the beating heart of the 3I Atlas mystery. It is the reason why scientists are forced to entertain possibilities that would otherwise be dismissed. When basic, well-understood physics fails to explain an observation, you have no choice but to start asking uncomfortable questions. To properly frame the potential of 3I Atlas, we must fully grasp the concept of a black swan. The term was popularized by philosopher and statistician Nassim Nicholas Taleb to describe events that lie outside the realm of regular expectations, carry an extreme impact, and, in hindsight, are often falsely rationalized as being predictable. The 2008 financial crisis is a classic example. Experts assured everyone the system was stable, and then it collapsed, after which everyone could see the warning signs that were previously dismissed as noise. A black swan is, by its very nature, unrecognizable until after it has happened and the world has irrevocably changed. So, how do we translate this abstract concept into the concrete realm of astronomy and solar system threats? What would constitute a true black swan event in space? I propose a working set of criteria. A space-based black swan must exhibit at least 3 of the following 4 characteristics. First, unpredictability beyond current models. It must be genuinely outside the parameter space of our existing theories, not just a rare statistical outlier. Second, high potential impact. It must have the capacity to drastically affect planetary safety, scientific understanding, or humanity's perception of its place in the cosmos. Third, irreversible consequences. Its effects must be lasting, orbit shifts that persist for millennia, a loss of data integrity, or a new understanding that invalidates old textbooks. Fourth, evidence of intentionality or physics. Anomalies. It must show signs that cannot be explained by natural randomness, such as a signal that defies astrophysical processes or a trajectory correction that defies inertia. Now let's apply this framework to 3I Atlas as it stands today. Is it unpredictable? Its behavior is certainly at the very edge of our models, but is it truly beyond them? Debatable. Does it have high potential impact? Scientifically, yes, but it poses no direct, immediate threat to Earth. Does it show irreversible consequences? Not yet. Is there evidence of intentionality? None that we have detected. So by this strict definition, 3I Atlas is not currently a Black Swan event. But, and this is the critical but, it could become one. If it were to do something truly unexpected in the coming days, weeks, or even years, we would look back and say, the seeds were sown now. This is the paradox we face. We can only identify a black swan in hindsight, so our only defense is to build robust systems and maintain a mindset that treats the improbable as worthy of investigation. Given this framework, I've identified 8 specific scenarios through which 3I Atlas could transition from a curious anomaly into a full-blown black swan. These scenarios range from the scientifically grounded to the wildly speculative, but each represents a different flavor of paradigm shift, a different path from cosmic curiosity to global crisis. We will explore each in detail, but let us preview them now to understand the landscape of possibility. Scenario 1, orbital domino. A small gravitational nudge from 3I Atlas on a passing asteroid or moon cascades over decades into a significant orbital shift, potentially creating a future impact threat we never saw coming. Scenario 2, fragmentation event. The comet breaks apart, but one fragment behaves anomalously, decelerating against the outgassing direction or changing course in a way that suggests internal structure or propulsion. Scenario 3, solar disruption. The comet's perihelion passage coincides uncannily with a massive coronal mass ejection or solar flare aimed at Earth, disrupting satellites and power grids, forcing us to question if it was mere coincidence or something more. Scenario 4, artificial signal. Radio telescopes detect a brief, structured pulse of emission from the object, a signal buried in noise that, if confirmed, would confirm we are not alone. Scenario 5, atmospheric anomaly. The comet's passage triggers unexpected disturbances in Earth's or Mars's ionosphere, subtle spikes in electron density, GPS delays or unseasonal auroras, suggesting an unknown interaction between cometary material and planetary magnetospheres. Scenario 6, disclosure cascade. A slow drip of information from space agencies involving quiet meetings, re-released archival data, and coordinated statements suggest that something unexpected was found, initiating a soft, controlled disclosure process. Scenario 7, psychological singularity. Mass attention and speculation create a social and political cascade where belief itself drives real-world consequences, funding shifts, policy changes, and panic, making the object significant not for what it is, but for what we believe it to be. Scenario 8, reality glitch. Multiple independent instruments record slight timing anomalies in pulsar data, atomic clocks, or spacecraft telemetry, all aligned with the comet's passage, hinting at a disturbance in space-time itself or a flaw in our fundamental understanding of time. This is our map of the unknown. Over the next hours, we will examine each of these paths, assessing their plausibility, their evidence, and their consequences. Let's begin with the most physically plausible and insidious of the scenarios, the orbital domino. This is the nightmare that keeps planetary defense experts awake at night, not because it is likely, but because its consequences are delayed, obscured by time, and by the time they manifest, it is too late to intervene. The scenario is rooted in the chaotic nature of orbital mechanics. Orbits are exquisitely sensitive to initial conditions. A tiny change in velocity today can compound over decades into a massive change in position. 3i Atlas, with the mass of a small mountain, traveled through the inner solar system. On October 3, 2025, it passed within 0.19 AU of Mars, a close encounter by any measure. While its gravitational pull on Mars itself was negligible, its influence on smaller bodies in the vicinity, the Martian moons Phobos and Deimos, or co-orbital Trojan asteroids, was not zero. Imagine it exerted a gravitational tug on a small, hitherto unnoticed asteroid, changing its velocity by a mere millimeter per second. That is infinitesimal, utterly undetectable with our current technology. But over 10 orbital periods, 30, 40, 50 years, that millimeter per second translates into a positional shift of hundreds of thousands of kilometers. If that asteroid was on a potentially hazardous trajectory, that tiny nudge could be the difference between a miss and a direct impact with Earth. The terrifying part of this scenario is the causal opacity. We do not have a complete catalogue of every small body in the solar system, and we certainly do not track the gravitational perturbations from interstellar visitors on these unknown objects. If in 2060 an asteroid appears on a collision course, we will have no way to trace its path back to the gravitational influence of 3i Atlas in 2025. The connection will be lost in the noise of a chaotic system. It would be a black swan in the truest sense, an event with extreme impact, completely unpredictable with our current models, whose cause only becomes obvious in hindsight, if at all. Our planetary defense networks are built to detect known threats, not to model every possible gravitational interaction from passing interstellar objects. This scenario exposes a critical gap in our long-term security. The second scenario, the fragmentation event, moves from the delayed threat of orbital chaos to a more immediate and observable anomaly. Comets fragment all the time. It is one of their most common behaviors. Thermal stress from the sun, rotational forces, and subsurface pressure buildups can cause a nucleus to split apart. We have witnessed this repeatedly, from the spectacular breakup of Comet Shoemaker-Levy 9 before it struck Jupiter, to the ongoing disintegration of Comet 73P Schwarzmann-Wachmann. So fragmentation itself is not anomalous. What would be anomalous is the behavior of a fragment. Imagine that in the weeks following perihelion, astronomers detect a secondary brightness spike, confirming that a piece has broken off from 3i Atlas. They begin tracking this fragment, calculating its expected trajectory based on the velocity imparted during the breakup. But the numbers don't work. The fragment is not moving as predicted. Perhaps it is decelerating when it should be accelerating, or it changes direction in a way that cannot be explained by the asymmetric thrust of outgassing jets. This would be deeply strange. To explain it naturally, we would have to invoke complex internal structures, cavities that channel gas in specific directions, or a peculiar tumble that creates unexpected thrust vectors. But what if even those natural explanations fall short? What if the fragment's motion suggests a degree of control, a directed quality that hints at something other than passive, natural forces? This is the territory where speculation runs high. I'm not saying this is likely, but if it were to occur, it would force a fundamental re-evaluation of what 3i Atlas actually is. Investigating such a fragment would be a monumental challenge. As the object moves away from the sun, it grows fainter. Telescopes would struggle to resolve detail. Spectroscopy could tell us about its composition, but not its internal structure. Radar imaging, which can reveal surface features and rotation, is only possible if the fragment passes close enough to Earth. The window for gathering conclusive data is short, and once it closes, the fragment becomes just another dim speck of data. Its anomalous behavior, an unresolved question mark in the archives, a potential black swan that flickered and vanished before we could understand it. Scenario 3. Solar disruption ventures into territory that mainstream astrophysics largely dismisses, but which captures the imagination due to the sheer scale of the potential consequences. The Sun is a seething ball of plasma, a chaotic system where magnetic fields twist, reconnect, and unleash titanic amounts of energy in the form of solar flares and coronal mass ejections, CMEs. When a CME is directed at Earth, it can compress our magnetosphere, induce powerful currents in power grids, potentially causing widespread blackouts, damage satellites, and create brilliant auroras. The Carrington event of 1859, the most powerful geomagnetic storm on record, caused telegraph systems to fail and sparks to fly from pylons. A similar event today could cause trillions of dollars in damage and cripple modern infrastructure. The question at the heart of this scenario is, could 3I Atlas's perihelion passage trigger or influence such an event? The established scientific consensus is a firm no. The comet is far too small, its mass negligible compared to the Sun, its gravitational and magnetic influence essentially zero. There is no known physical mechanism for a comet to cause a solar eruption. However, let's explore the fringes of second-order effects. As 3I Atlas approached the Sun, its outgassing created a vast, ionized coma, a cloud of electrically conductive plasma. Could this plasma cloud, as it passed through the Sun's complex magnetic field, act as a trigger for an instability that was already building in the corona? Could it serve as a catalyst, a seed around which a CME could form? It is a long shot, a hypothesis that sits on the very edge of plausibility. But if a significant solar event, a major X-class flare, or a powerful Earth-directed CME did occur on or around October 29, 2025, the timing would be undeniably striking. It would be a correlation that demands investigation, even if causation remains unproven. The absence of such an event during this perihelion does not completely invalidate the scenario for future interstellar visitors. It merely means it did not happen this time. The black swan potential here lies in the coincidence of timing and the catastrophic impact a major solar storm would have on our technology-dependent civilization. It forces us to ask whether our understanding of solar physics is complete or if there are subtle, unknown interactions between the Sun and incoming bodies that we have simply never had the data to observe before. Scenario 4. The artificial signal is the one that carries the highest stakes of all. It is the scenario that invites ridicule from skeptics and fervent hope from enthusiasts, for it deals with the possibility of contact. The search for extraterrestrial intelligence, SETI, has scanned the skies for decades, listening for narrowband radio signals or looking for laser pulses that would betray the presence of another technological civilization. Thus far, the results have been silent, save for a few tantalizing but unconfirmed anomalies like the famous "wow" signal. SETI strategies often assume that a broadcasting civilization would want to be heard, transmitting powerful, repeating signals over long periods. But what if that assumption is wrong? What if 3I Atlas is not a natural object but a probe, and its communication strategy is not about broadcasting but about stealth? Imagine it emitted a single, brief radio pulse during its perihelion passage. A pulse lasting only seconds, centered on a meaningful frequency like the 1.42 GHz hydrogen line, its strength barely above the background noise. Our radio telescopes would have recorded it, but automated data processing pipelines, designed to filter out human-made radio frequency interference and random noise, would have likely flagged it and discarded it. It would have been dismissed before a human eye ever saw it. Now imagine years from now a researcher runs archival data from October 2025 through a new, more sophisticated machine learning algorithm. This algorithm, unbiased by human expectations, finds the pulse. It identifies a structured, non-random signal originating from the precise direction of 3I Atlas at the precise moment of its closest approach to the Sun. The implications are staggering. It would suggest not only that we are not alone, but that we have been visited, and we missed it because our filters were tuned to find what we expected, not what was actually there. The dilemma then becomes, what do we do with this information? Do we announce it to the world knowing it cannot be confirmed or repeated, and risk global panic, conspiracy theories, and a crisis of faith in science? Or do we bury it, deeming the evidence too ambiguous and the potential social consequences too severe, thereby participating in the very cover-up that conspiracy theorists have always alleged? This scenario is a black swan not just of discovery, but of response. It tests our readiness not only technologically but also psychologically and politically for the moment we find we are not the only sentient beings in the universe. Pulling our gaze back from the depths of space and the possibility of intelligence, Scenario 5, the atmospheric anomaly, focuses on effects within our own planetary backyard. High above our heads, between 100 and 1,000 kilometers in altitude, lies the ionosphere, a layer of Earth's atmosphere that is ionized by solar radiation. This tenuous plasma is crucial for long-range radio communication, as it reflects certain frequencies, and it also affects the accuracy of GPS signals, which must pass through it. The ionosphere is notoriously sensitive, fluctuating with the sun's activity, but also responding to more local events, such as meteor showers, whose vaporized material can create transient layers of enhanced ionization. The question is, could the passage of 3I Atlas have caused a detectable ripple in this invisible ocean? The comet itself was never close to Earth, passing no nearer than about 1.2 AU. However, a comet's ion tail, composed of charged particles pushed by the solar wind, can stretch for millions of kilometers. Could that tenuous stream of plasma have briefly brushed against Earth's magnetosphere? If so, it could have funneled charged particles down magnetic field lines, causing a subtle, transient spike in ionospheric electron density. The effects would be minor, perhaps a slight, unusual delay in GPS signals, a brief anomaly in radio propagation, or a faint, unexpected auroral glow detected by sensitive instruments. On Mars, the case is even more intriguing. During its October 3rd close approach, 3I Atlas passed within 0.19 AU of the red planet. Mars has a thin atmosphere and a patchy, localized magnetic field, but it does have an ionosphere and experiences auroras. Orbiters like MAVEN are equipped to study such phenomena. Did any of their instruments detect a transient spike in ion density, a peculiar auroral event, or an unexplained fluctuation in the Martian upper atmosphere coinciding with the comet's flyby? The data likely exists, but it may be sitting in an archive, unanalyzed in this specific context. No one may have thought to look for a connection between an interstellar comet and the Martian ionosphere. This is a common theme with potential black swans. The data is often there, but the hypothesis to connect it isn't. An atmospheric anomaly would not be world-ending, but it would be significant. It would demonstrate a previously unknown interaction between interstellar objects and planetary environments, suggesting that our understanding of space weather and atmospheric physics is incomplete, and that even distant, non-threatening visitors can leave a faint, scientific fingerprint on our world. Scenario 6, the disclosure cascade, moves from the realm of pure physics into the murky waters of information, psychology, and institutional behavior. It is not about what 3I Atlas is, but about what we know about it and when we know it. The International Asteroid Warning Network, IAWN, publicly coordinated an observation campaign for 3I Atlas. This is normal scientific procedure for an object of interest and demonstrates international cooperation, not conspiracy. But let's consider a more nuanced possibility. What if, during this coordinated observation, several space agencies or research institutions detected minor, puzzling anomalies? Not a smoking gun, but a series of small discrepancies. Perhaps a Mars orbiter recorded a tiny, unexplained timing offset in its telemetry during the close approach. Perhaps deep space antennas tracking other missions detected similar microsecond glitches. Perhaps archival data from previous interstellar object flybys, when reanalyzed, showed similar, previously dismissed quirks. Individually, each piece of data is meaningless, well within error margins. But collectively, to a trained eye inside the agencies, they form a faint pattern. This pattern is concerning enough to trigger internal memos, the formation of quiet working groups and closed-door meetings to discuss the findings and determine a public response strategy. The result would not be a single, dramatic press conference announcing we are not alone. Instead, it would be a slow, controlled cascade of information. A previously unreleased dataset is published with a new, more detailed analysis. A scientific paper appears cautiously discussing unexplained phenomena associated with hyperbolic objects. A high-level official gives a carefully worded interview emphasizing the need for further study. Each event is explainable and defensible on its own, but together they form a narrative of growing awareness and controlled revelation. This is a 21st century disclosure, a process, not an event. If we are inside such a cascade right now, we would not recognize it in real time. We would only connect the dots in hindsight, looking back at the timeline of data releases, statements, and research priorities. The black swan here is not the object itself, but the slow, irreversible shift in human knowledge it precipitates, managed by institutions trying to balance truth with stability. It asks a profound question. If the truth were too destabilizing, would we even be told? Or would we be guided toward it so slowly that we never felt the shock? Scenario 7, the psychological singularity, is perhaps the most meta of all the scenarios, for it deals with the power of human belief to shape reality. This scenario posits that the true impact of 3i Atlas will not come from its physical properties, but from our collective psychological and social response to it. History is replete with examples. In 1910, as Halley's Comet approached, widespread fear that Earth would pass through its cyanogen-filled tail led to panic, with entrepreneurs selling comet pills and people sealing their windows. The threat was non-existent, but the public belief created very real social and economic effects. The Y2K scare saw billions spent on mitigating a computer bug that, in the end, caused minimal disruption, but the fear and preparation were very real. Now apply this to 3i Atlas. The media coverage, the scientific debate, the online speculation, all of it is fueling a narrative of mystery and potential threat. Social media algorithms amplify the most sensational theories. Forums are alight with analysis and anxiety. People report dreams and synchronicities related to the comet. When scientists issue cautious statements saying there is no evidence of danger instead of it is absolutely safe, that linguistic hedge is interpreted by a fearful public as doubt, as hidden knowledge. This perception gains momentum. Concerned citizens contact their representatives. Journalists demand answers. Policymakers, sensitive to public sentiment, begin to ask questions. Suddenly, space agencies and defense departments are forced to devote time and resources to addressing the perception of a threat, not an actual threat. Telescope time is reallocated from other projects to continuously monitor 3i Atlas. Planetary defense budgets are debated in congresses and parliaments. International task forces are convened. The object, through no action of its own, becomes a significant driver of policy and funding. It achieves sociological significance. This is a self-fulfilling prophecy where belief creates concrete consequences. The Black Swan Event is not in the sky but in our own minds. It reveals the fragility of our social systems in the face of widespread uncertainty and the power of narrative in the digital age. The greatest threat from the cosmos may not be rocks or radiation, but our own innate tendency to see patterns and project meaning, and the cascading effects that can have on a globalized, interconnected civilization. The final scenario, the reality glitch, is the most speculative, venturing into the frontiers of fundamental physics. It proposes that 3i Atlas's passage could reveal or create subtle anomalies in the very fabric of our measurement of reality, specifically in the realm of time. Our modern technological civilization is built on the bedrock of precise timekeeping. Atomic clocks, accurate to nanoseconds, synchronize our GPS satellites, financial networks, and communication systems. Pulsars, the spinning remnants of dead stars, serve as cosmic lighthouses with breathtaking regularity, their pulses used by astronomers as natural clocks to detect the ripples of gravitational waves. This scenario asks, What if multiple independent timing systems recorded minute but correlated anomalies during the perihelion passage of 3I Atlas? Imagine a postdoctoral researcher years from now analyzing pulsar timing data from October 2025. They are looking for the faint signature of merging supermassive black holes, but they notice something else, a cluster of tiny timing residuals, pulses that arrived a few nanoseconds early or late, across several different pulsars, all during the same week in late October. Separately, an engineer reviewing telemetry from deep space probes notices similar, slight timestamp discrepancies in the data streams from that period. On Earth, the logs of atomic clock networks show a barely perceptible synchronized drift. Each of these anomalies is, on its own, dismissed as noise, instrumental error, or propagation effects through the interstellar medium. But together they form a pattern that is correlated in time with the comet's passage.
What could this mean? There is no known mechanism.
The comet's gravity is far too weak to cause relativistic time dilation. Perhaps its ionized coma created a localized plasma environment that affected the propagation speed of radio signals in a way we haven't modeled. Or, in the most extreme interpretation, it could hint at something deeper, a slight wrinkle in space-time itself associated with the object's passage, or a revelation that our understanding of time or signal propagation is flawed in ways we cannot yet conceive. This scenario is a black swan not of impact, but of understanding. It would not knock out our power grids, but it would shake the foundations of physics, suggesting that the universe operates with a layer of complexity or subtlety that our current models completely miss. It is the ultimate reminder that our knowledge is provisional, and that the cosmos may still hold surprises that challenge our most fundamental assumptions. The enigmatic nature of 3I Atlas has exposed a fundamental rift within the scientific community and in the media that amplifies its voice. On one side stands the cautious establishment, represented by scientists like NASA's lead scientist for small bodies, Tom Statler, who has gone on record stating that 3I Atlas, for all its peculiarities, behaves like a comet. He points to the clear evidence of water outgassing, dust production, and activity consistent with sublimation. From this perspective, it is a natural body, albeit an extreme one, and its anomalies are simply puzzles to be solved within the existing framework of cometary science. The emphasis is on caution, on avoiding sensationalism, and on the slow, methodical process of data collection and peer review. On the other side of this divide are the iconoclasts and the speculators, led by figures like Avi Loeb. Loeb's approach is to take the anomalies at face value and ask what they could mean if they are not explainable by standard models. He champions the idea of unexplained phenomena as a legitimate category of scientific inquiry, arguing that dismissing anomalies out of hand is antithetical to the scientific spirit. This camp is willing to entertain more exotic possibilities, including the idea that the object could be a piece of alien technology, a derelict probe, or a fragment from a civilization that harnessed the power of its star. The media, of course, thrives on this tension. Headlines swing between bizarre interstellar comet baffles scientists and experts say alien comet claims are unfounded. This creates a confusing information environment for the public. Who is right? The truth likely lies somewhere in the vast, unexplored middle ground. 3I Atlas is almost certainly a natural object, but its specific combination of properties, extreme CO2 richness, early activity, and the acceleration discrepancy may point to a formation environment so alien to our own that it produces behavior we have never seen before. It is a messenger from a star system with a different chemical history, a different thermal environment, a different everything. The divide is not really about the object itself, but about methodology. The establishment seeks to fit it into known categories, while the speculators are willing to create new categories to accommodate it. Both approaches are necessary for scientific progress. One provides the bedrock of reliable knowledge, the other the spark of revolutionary discovery. The single greatest obstacle to resolving the mystery of 3i Atlas is a profound data gap. We are trying to understand a complex three-dimensional object millions of kilometers away using only the faint light it reflects and emits. This light is our only messenger, and it carries a limited amount of information. The most critical unknown is the size and shape of the nucleus. All our estimates are indirect, based on the object's brightness and assumptions about its reflectivity, or albedo. If the nucleus is dark, like the nucleus of Comet 67P to Churyumov-Gerasimenko, it must be larger to reflect the amount of light we see. If it is bright, like the surface of Enceladus, it could be much smaller. This uncertainty spans an order of magnitude from 0.3 km to 5.6 km. This single parameter affects everything: the density, the mass, the strength of the outgassing relative to the object's gravity, and the interpretation of the non-gravitational acceleration. Without knowing the size, we are trying to solve an equation with two variables. We also lack direct imaging of the nucleus. The Hubble Space Telescope and other large observatories have tried, but at its closest, the object was still too far away and too active for the nucleus to be resolved from its bright, dusty coma. It remains a point of light. We do not know if it is a single solid body, a loose rubble pile, a contact binary like Oumuamua was theorized to be, or something even more exotic. We do not know its rotation period or its axial tilt, which are critical for modeling how outgassing jets affect its spin and trajectory. The composition data from JWST is invaluable, but it gives us an average of the entire coma, not a detailed map of the surface. Are there localized vents spewing different chemicals? Is the surface heterogeneous?
We have no idea.
This data gap is not due to negligence. It is a fundamental limitation of our current technology for observing small, distant, and fast-moving objects. It means that for all our analysis and speculation, we are largely operating in the dark, inferring the nature of an elephant by touching its tail. This inherent uncertainty is the fertile ground in which all the Black Swan scenarios can grow. Until we can send a probe to rendezvous with an interstellar object, a mission, concept being studied, but years from realization, we will always be left with more questions than answers when one of these visitors
Streaks through our system. To fully
appreciate the significance of 3i Atlas, we must place it in the context of its famous predecessor, the first known interstellar object, 1i Oumuamua. Discovered in October 2017, Oumuamua was a true trailblazer, proving that such visitors were not just theoretical, but a regular, if infrequent, feature of our solar system's ecology.
And like 3i Atlas, it was deeply strange.
Oumuamua was an elongated, likely cigar-shaped object tumbling through space. It showed no visible coma or tail, classifying it as an asteroid, not a comet. Yet, it exhibited a small but significant non-gravitational acceleration that could not be explained by outgassing, as no outgassing was detected. This is the inverse of the 3i Atlas problem. Atlas has too much outgassing for its acceleration. Oumuamua had acceleration with no visible outgassing. To explain Oumuamua, scientists had to get creative. Some proposed it was a hydrogen iceberg that outgassed hydrogen, which is invisible to our telescopes. Others suggested it was a nitrogen iceberg fragment from a Pluto-like world in another system. And of course, Avi Loeb famously proposed it could be a light sail, a piece of alien technology using radiation pressure for propulsion. The debate over Oumuamua remains unresolved. It vanished before we could gather more data, leaving behind a legacy of mystery and a new scientific field, the study of interstellar objects. Now, with 3i Atlas, we have a second data point. It is different from Oumuamua in almost every way. It is clearly a comet with a massive coma and tail, yet it shares the same core characteristic. It doesn't fit neatly into our boxes. It challenges our assumptions. The existence of two such different yet both anomalous interstellar objects suggests a profound possibility. that the galaxy is filled with a far greater diversity of small bodies than we ever imagined. Our own solar system, with its comets and asteroids, may represent just one narrow slice of the possible planetary architectures and formation histories. Oumuamua and 3I Atlas are like 2 pages torn from 2 completely different books in a vast cosmic library. We have only just learned to read, and we are already discovering that the stories out there are wilder than anything we could have written ourselves. The back-to-back mysteries of Oumuamua and 3I Atlas have galvanized the astronomical community. It is now clear that interstellar objects are not rare flukes, but a constant, if sparse, drizzle of material from other star systems. Current estimates suggest that at any given time there is likely one Oumuamua-sized object within the orbit of Neptune. This realization has opened up an entirely new frontier in astronomy, the detailed study of exosystem planetesimals. These objects are the only tangible pieces of other solar systems we will ever get our hands on, or at least our telescopes on. They carry the chemical and physical imprint of their birthplaces, offering a way to perform comparative planetology without having to travel to other stars. In response, mission concepts are being actively developed. The most promising is the European Space Agency's ESA Comet Interceptor mission, scheduled for launch in 2029. Its primary goal is to park a spacecraft at the Earth-Sun L2 Lagrange point and wait. It will lie in wait, ready to be dispatched at a moment's notice to intercept a pristine, long-period comet from the Oort cloud, or, if we are lucky, a future interstellar object that is discovered early enough and on a favorable trajectory. Such a mission would be transformative. A flyby or even a rendezvous with an interstellar object would provide the data we so desperately lack: high-resolution images of the nucleus, direct mass measurements, in situ analysis of the comet's composition, and a detailed map of its surface properties. It would answer the questions that haunt us about 3I Atlas and Oumuamua.
Was Oumuamua a nitrogen iceberg?
Is 3I Atlas's nucleus a monolithic chunk of ice or a fragile aggregate? What is the true cause of the anomalous accelerations? Beyond the comet interceptor, more ambitious concepts are on the drawing board, involving rapid response launch vehicles and advanced propulsion to chase down these fast-moving targets. The study of interstellar objects is transitioning from a passive, observational science to an active, exploratory one. We are no longer content to just watch them pass by. We want to meet them, to study them up close, and to read the stories they carry from the stars. The enduring mystery of 3I Atlas and Oumuamua inevitably forces us to revisit the oldest and most profound question in astronomy: where is everybody? This is the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial intelligence and the lack of any observable evidence for it. For decades, SETI has focused on searching for electromagnetic signals, radio waves, or laser pulses. But what if this strategy is flawed? What if advanced civilizations do not broadcast their presence, but instead fill the galaxy with passive, silent artifacts? This is the artifact hypothesis for resolving the Fermi paradox. In this view, the galaxy could be teeming with the detritus of dead civilizations, or with autonomous probes sent out eons ago to monitor star systems for signs of life. These artifacts would not transmit. They would simply exist, drifting on the galactic currents, their purpose long forgotten or suspended, waiting for a trigger. From this perspective, objects like Oumuamua and 3I Atlas take on a new and startling significance. They would no longer be just natural curiosities, but potential candidates for such artifacts. Their anomalous properties, the lack of outgassing but presence of acceleration for Oumuamua, the extreme outgassing but lack of acceleration for 3I Atlas, could be the subtle signatures of their artificial nature, signatures we lack the context to interpret correctly. Perhaps they are not functional probes, but Broken ones, their systems failing, their structures degrading, producing the puzzling physical data we observe. Or perhaps they are working exactly as intended, and their mission is simply to pass through, to gather data passively, and to report back to some central repository we cannot detect. This line of thinking is, of course, highly speculative and sits firmly in the realm of the unproven. But the Fermi paradox demands that we consider all possibilities. If interstellar travel is prohibitively expensive for biological beings, perhaps sending small, durable, long-lived probes is the most efficient way to explore the galaxy. If that is the case, then our solar system should be periodically visited by them. We may have been looking for a phone call when the evidence was floating right past our doorstep all along. 3i Atlas, in this grandest of scenarios, is not a black swan for our solar system, but a potential data point in a much larger, galactic-scale mystery. The journey of 3i Atlas is not confined to scientific journals and telescope control rooms. It has begun to ripple through our culture, demonstrating how a celestial event can capture the global imagination and influence art, philosophy, and society. Online, communities have sprung up dedicated to analyzing every new data release. Amateur astronomers share their images and light curves. Forums buzz with theories ranging from the rigorously scientific to the wildly conspiratorial. The object has become a blank canvas upon which we project our hopes, our fears, and our understanding of the universe. Artists are creating stunning visualizations of what the nucleus might look like. Writers are drafting stories inspired by its mystery. Philosophers are using it as a case study to discuss the limits of human knowledge and our preparedness for cosmic-scale discoveries. This cultural absorption is a critical part of the story. It shows a public hunger for cosmic mystery, a desire to look up from our terrestrial concerns and contemplate the vastness and strangeness of the cosmos. It is a modern-day version of the awe that ancient civilizations felt when a comet appeared in their skies, an awe that drove them to create myths and seek meaning in the heavens. However, this cultural impact has a darker side. The same mystery that inspires art can also fuel misinformation and anxiety. Sensationalist media outlets can distort complex scientific debates into binary aliens versus comet arguments. This can erode public trust in scientific institutions and create a climate where evidence is secondary to narrative. The story of 3i Atlas, therefore, is also a story about science communication in the 21st century. It highlights the challenge of conveying uncertainty and nuance in a media environment that craves simple, definitive answers. It forces scientists to be not just researchers, but also educators and communicators tasked with guiding the public through a landscape of fascinating, yet inconclusive, data. The societal impact of 3i Atlas, regardless of its ultimate nature, will be lasting. It has already become a symbol, a reminder that we live in a dynamic,
interconnected cosmos and that the unknown is not something to be feared,
but to be explored. While 3i Atlas poses no direct economic threat, its passage has real, quantifiable costs and highlights the economic implications of planetary defense and deep space exploration. The most immediate cost is the allocation of scarce scientific resources. Hubble, JWST, the Very Large Telescope, and dozens of other ground-based observatories have devoted hundreds of hours of precious observation time to tracking and analyzing this object. This is time that could have been spent studying exoplanet atmospheres, probing distant galaxies, or monitoring near-Earth asteroids. The decision to prioritize 3i Atlas represents an opportunity cost, a calculation by telescope time allocation committees that the potential scientific return from this interstellar visitor outweighs that of other projects. Beyond direct observation, there is the cost of analysis. Scientists at universities and research institutions around the world are spending countless hours reducing the data, running models, and writing papers. This represents a significant investment of human capital and intellectual energy, funded by government grants and institutional budgets. Is this a wise investment? From a pure knowledge standpoint, absolutely. Understanding the composition and behavior of interstellar objects is a fundamental scientific question. But from a narrow economic perspective, it is a cost with no immediate, tangible return. The story of 3I Atlas also underscores the economic case for improved planetary defense. The orbital domino scenario, while unlikely, illustrates a class of threat that our current detection networks are not designed to handle. Developing the capability to track the long-term gravitational perturbations from passing interstellar objects would require a more comprehensive and sensitive survey of the solar system, a multi-billion-dollar endeavor. Furthermore, the interest in missions like the Comet interceptor shows a willingness to invest significant capital, hundreds of millions to billions of dollars, in the proactive exploration of these objects. This is not just science for science's sake. It is an investment in our long-term future, in our ability to understand and navigate a cosmos that is far more dynamic and interconnected than we once believed. The economic angle reminds us that the pursuit of knowledge has a price tag, but that the cost of ignorance when it comes to threats from space could be infinitely higher. At its core, the mystery of 3I Atlas is a psychological challenge. It forces us, as individuals and as a species, to confront the limits of our understanding and to sit with uncertainty. Human brains are pattern recognition machines, evolved to find causes for effects in our immediate environment. When faced with a phenomenon that resists easy explanation, we experience cognitive dissonance. We feel an intense drive to resolve the uncertainty, to find a label, to put the object in a box, any box, so that our mental model of the world can be restored to equilibrium. This drive explains the polarization in the discourse. Some cling fiercely to the "it's just a comet" explanation, dismissing any anomalies as measurement error or incomplete models. Others leap to the "it's an alien probe" explanation because it provides a neat, if extraordinary, resolution to the mystery. Both are coping mechanisms for the same underlying discomfort, the discomfort of not knowing. This psychological dimension is amplified by the scale involved. This is not a mystery in a laboratory or a crime scene. It is a mystery unfolding on a cosmic stage. The stakes feel implicitly higher. If we are wrong about the nature of this object, it feels like we could be wrong about our fundamental place in the universe. The Copernican principle taught us we are not the center of the universe. Darwin taught us we are not separate from the animal kingdom. Now, interstellar objects like 3I Atlas whisper that we may not even be the sole or the most advanced actors in the cosmic drama. Grappling with this requires a psychological maturity that our species is still developing. It requires the humility to say, we don't know, the patience to wait for more data, and the courage to follow the evidence wherever it leads, even if it leads to conclusions that are unsettling or paradigm-shattering. The story of 3I Atlas is, in many ways, a test of our collective psychological readiness for a universe that is far stranger and more
wonderful than we have ever allowed ourselves to. Imagine the media has played
a dual and often contradictory role in the story of 3I Atlas, acting as both an essential conduit of information and an amplifier of mystery and, at times, misinformation. On the positive side, responsible science journalism has brought this fascinating story to a global audience. Outlets like Nature, Science, and dedicated science communicators on YouTube and in print have done the hard work of translating complex astrophysical concepts into language the public can understand. They have interviewed the key scientists, explained the nuances of the debate, and highlighted the genuine, exciting mysteries at the heart of the story. This has democratized access to cutting-edge science and fostered a sense of public engagement with a live, unfolding discovery. However, the media ecosystem also has an inherent bias toward conflict and sensationalism. The measured, cautious statements of establishment scientists often make for less compelling copy than the bold, provocative speculations of figures like Avi Loeb. This can create a false balance, where a minority viewpoint is given equal or greater weight than the scientific consensus. not because of its evidential support, but because of its dramatic appeal. Headlines that ask, "Is this an alien spacecraft?" generate more clicks than those that state, "Scientists puzzled by Comet's composition." This dynamic can distort the public's perception of the scientific process. It can make it seem as if the scientific community is deeply divided and on the verge of a monumental discovery, when in reality, the vast majority of researchers are calmly collecting data and testing hypotheses within a natural framework. The media's role as an amplifier means that the social reality of 3I Atlas is often more dramatic and polarized than its scientific reality. This places a heavy burden of responsibility on both journalists and consumers. Journalists must strive for accuracy and context over sensationalism. Consumers must develop the media literacy to distinguish between evidence-based reporting and speculative entertainment. In the age of information, understanding how a story is told is almost as important as understanding the story itself. The enduring anomalies of 3I Atlas force us to confront a deep philosophical question. What do we mean by natural? In our current paradigm, natural is defined as phenomena that can be explained by the known laws of physics and chemistry without the need for intelligent agency. A comet is natural. A spacecraft is artificial. But what if we encounter an object that blurs this distinction? What if a civilization becomes so advanced that its technology is indistinguishable from the natural world? This is the concept of post-biological or post-technological artifacts. An object like 3I Atlas, if it were an alien probe, would not necessarily look like a shiny metal spaceship from a science fiction movie. After millennia of travel through interstellar space, battered by cosmic rays and micrometeoroids, its surface would be weathered, pitted, and covered in a layer of cosmic dust. It might look, for all intents and purposes, like a comet or an asteroid. Its propulsion system might not be a fiery rocket, but a subtle manipulation of space-time or a solar sail. Its unnatural quality would not be in its appearance, but in its behavior, in the subtle discrepancies between its observed actions and the predictions of our models for natural objects. This forces an expansion of the definition of natural. Perhaps intelligence is a natural force in the universe, as much a part of cosmic evolution as gravity and nuclear fusion. Perhaps the products of intelligence, technology, represent a new class of physical object, one that obeys the laws of physics but utilizes them in ways that unintelligent nature, through random processes, rarely or never does. The philosophical implication of 3I Atlas is that our clean categories of natural and artificial may be a provincial, human-centric distinction. The cosmos may not care about our categories. It may simply produce a continuum of phenomena, from rocks to comets, to biological beings, to technological civilizations, all part of a single, complex, evolving universe. To truly understand what we are seeing, we may need to abandon our preconceived notions and develop a new, more inclusive science, one that is capable of recognizing the signature of intelligence, not as something supernatural, but as a natural, if rare, cosmic process. Regardless of how the specific mysteries of 3I Atlas are eventually resolved, its long-term legacy is already secure. It represents a turning point in astronomy, the moment the study of interstellar objects moved from a theoretical curiosity to a mainstream, urgent field of research. Oumuamua was the proof of concept. 3I Atlas is the confirmation of diversity and anomaly. Future history books will likely mark the period from 2017 to the present as the dawn of interstellar object science. The data gathered on 3I Atlas, its spectrum, its light curve, its trajectory, will be pored over for decades, a benchmark against which future interstellar visitors will be compared. Every new object discovered will be measured against the strange standards set by Oumuamua and Atlas. Are they CO2 rich? Do they show anomalous acceleration? Do they become active at great distances? We are building a statistical sample, one object at a time, and 3I Atlas is a critical, foundational data point in that sample. Its legacy will also be institutional. It has strengthened the case for missions like the Comet Interceptor. It has prompted space agencies to develop better protocols for the rapid response observation of fast-moving targets. It has inspired a new generation of astronomers and engineers to think about how we can reach out and touch these visitors from other stars. The ultimate legacy of 3i Atlas may be that it shattered our complacency. For centuries, we studied the solar system as a closed system, with the sun, planets, and comets all forming from the same primordial cloud. Interstellar objects remind us that our system is not an island. It is part of a galactic ecosystem constantly exchanging material with its stellar neighbors. We are not isolated. We are connected to the galaxy in a tangible material way. 3i Atlas is a piece of that connection, a messenger that has traveled light years to deliver a simple, profound message. There is more, much more, than what we see in our own celestial backyard. As 3i Atlas recedes into the darkness, it leaves behind a trail of unanswered questions, a roadmap for future research. The primary question, of course, is the nature of the acceleration discrepancy. Can refined models of cometary outgassing, incorporating a more porous nucleus or different jet geometries, explain why the observed acceleration is so weak? Or does the solution require a more radical rethinking of the object's mass or density? The size and shape of the nucleus remain the holy grail. As the object moves away from the Sun and its activity presumably subsides, there may be a brief window where the nucleus becomes visible against a fading coma. The world's most powerful telescopes, including JWST and the upcoming Extremely Large Telescope, will be tasked with trying to resolve it, to finally pin down its dimensions and perhaps even its shape. Another critical question concerns its long-term trajectory. Precise tracking as it leaves the solar system will provide the final, most accurate data on any non-gravitational forces. Even a tiny, persistent acceleration will be measurable over months and years, and this data will be essential for constraining the models. We also need to look backward. Are there other, older interstellar objects in our archives that were misclassified? Could reanalyzing data from past surveys with new algorithms uncover more of these visitors, allowing us to build a statistical picture of their true diversity? And looking forward, when will the next one come? Automated sky surveys like the Vera C. Rubin Observatory, scheduled to come online soon, are expected to discover interstellar objects with much greater frequency, perhaps several per year. Each new discovery will be an opportunity to test the hypotheses generated by 3i Atlas. The road ahead is long and filled with both challenges and opportunities. The story of 3i Atlas is not over. It is merely the end of the first chapter. The data it has provided will fuel scientific debate and discovery for years to come. The passage of 3i Atlas serves as a powerful call for vigilance. It is a dress rehearsal, a test of our systems and our mindset for the next interstellar visitor, and the one after that. The next one could be on a direct collision course with Earth, or it could be even stranger, exhibiting behavior that makes 3i Atlas look mundane by comparison. Our first line of defense is improved detection. We need all-sky, continuous survey telescopes with the sensitivity to detect these small, fast-moving objects as early as possible. The earlier we find them, the more time we have to study them, and the more likely it is that an interceptor mission like Comet Interceptor could be dispatched for a rendezvous. Second, we need to develop a standardized international protocol for the rapid response observation of interstellar objects. This protocol should automatically trigger observations by the world's most powerful telescopes, ensuring that we capture the highest quality data during the brief window when the object is close and active. Third, we need to invest in the theoretical work. We need to model the formation of planetary systems around other stars to understand the possible diversity of comets and asteroids they can produce. We need to develop better models for cometary activity that can handle extreme compositions and structures. And we must continue to do the hard, speculative thinking about what signatures of technology might look like, so that if we ever see one, we are prepared to recognize it. Finally, and most importantly, we must cultivate the right mindset, one of open-minded skepticism. We must be skeptical of extraordinary claims without evidence, but we must also be open to extraordinary evidence when it presents itself. We must be willing to follow the data, even when it leads us out of our comfort zone and into the unknown. The cosmos has sent us two enigmatic messengers in less than a decade. It would be the height of arrogance to assume we have seen all the tricks it has up its sleeve. We must be ready for the next one. So after this deep dive through the data, the scenarios, and the implications, what is the final verdict on 3I Atlas? Based on the preponderance of evidence, the most scientifically conservative and likely conclusion is that it is a natural comet. The detection of water and carbon dioxide outgassing is powerful, direct evidence of volatile ices sublimating under solar heat. This is a process we understand, even if the specific ratios and intensities are extreme. The anomalies can likely be explained by a combination of factors: a very large,
massive nucleus that dampens the acceleration from outgassing,
a formation history in a carbon dioxide-rich protoplanetary disk, and a porous, fragile structure that allows for intense activity far from the Sun. It is an outlier, a statistical weirdo, but it probably still fits within the broad, expanding envelope of what we call a comet. The artificial probe hypothesis, while captivating, remains an inference to the best explanation only after all natural explanations have been exhausted.
and we are far from that point.
The data gaps are too large, the uncertainties too significant to jump to such a monumental conclusion. The history of science is littered with anomalies that were later explained by new physics or better observations within a natural framework. However, to dismiss the possibility entirely would be unscientific. The very fact that we can formulate the question, "Is it artificial?" is a testament to how far we have come. A century ago, the idea of objects from other star systems was pure speculation. Today we are detecting them, and we are sophisticated enough to contemplate that some of them might not be rocks. The final verdict, then, is not a binary one. It is a spectrum of confidence. We can be 95% confident it is a natural comet. We can be 4% confident it is a natural comet of a type so novel it forces a new classification. And we can, with all due scientific humility, reserve 1% for the possibility that it is something else entirely, something that would force us to rewrite not just the textbooks on comets, but the story of humanity itself. As we conclude this exploration, the image of 3I Atlas that emerges is not one of a threat, but of a teacher. It has taught us humility, reminding us that for all our knowledge, the universe is still capable of surprising us. It has taught us the value of curiosity, driving scientists to devote countless hours to understanding a single, faint speck of light. And it has taught us the importance of perspective, lifting our gaze from our terrestrial squabbles to the grand, interconnected dance of the cosmos. The story of 3I Atlas is a story in progress. The data is still being analyzed, new papers will be published, new theories will be proposed and debated. This is science in action, messy, uncertain, and utterly thrilling. It is a process, not a destination. The true value of 3I Atlas may not lie in the answers it provides, but in the questions it forces us to ask. It pushes us to improve our telescopes, to plan new missions, to refine our models, and to expand our imaginations. It is a catalyst for progress, a spark for the next great leap in our understanding of the universe and our place within it. So, as 3I Atlas continues its lonely journey back into the interstellar dark, we are left not with fear, but with a sense of wonder and anticipation. It is a reminder that we live in a universe of infinite possibility, a cosmos that is stranger, more varied, and more wonderful than we can possibly imagine. The mystery is not a problem to be solved, but a gift to be embraced. And the greatest discovery of all may be that the journey of exploration has only just begun.